When we think of data, we often think of a table, an array of rows and columns in which the rows correspond to items of data, people, houses, cars, cities, counties, and the columns tell us what is known about those items. For people, for example, we might think of the columns containing last names, first names, ages, home addresses, income, or level of education. This traditional view of data is reinforced by the spreadsheet and by software products such as Microsoft's Excel. If the data include one or more columns that address the where question, such as home address, postal code, or latitude and longitude, then we call the data spatial. From this perspective, then, spatial data are no more than data with one or more extra columns addressing where. What's the big deal, you might ask? Why are spatial data more interesting, powerful, important, and problematic than any other data set? There are many answers to this question, and many reasons why GIS and spatial technologies deserve special attention and raise special issues. First and foremost is context. Knowing where allows us to tap other information about that location that can be helpful in understanding what is happening there. For example, many of the counties along the coasts of the United States experienced elevated rates of cancer of the throat and lungs among males in the years following World War II. One activity linking many of these counties was the construction of ships during the war, using large amounts of asbestos, a fact which led to the suspicion that exposure to asbestos could cause cancer, and to the subsequent banning of asbestos in construction. Another example of the special nature of spatial data occurs when the information being analyzed is aggregated. In the asbestos example, the data were aggregated by county in order to protect the confidentiality of individual health records. There are over 3,000 counties in the United States, and they're a very rich source of data on health, agriculture, demographics, and many other factors. But what if the analysis were repeated using some other spatial unit, such as states or watersheds or postal codes? Would we have reached the same conclusion? The answer is a definite no. The results of an analysis using aggregated spatial data will always change when the spatial units change. We call this the open shore effect or the Modifiable Areal Unit Problem, and it's something every spatial analyst must be aware of. Many of our methods of statistical analysis originated almost a century ago in fields such as experimental psychology and agronomy, where it was important to be able to reason from small samples of people or samples of a type of plant to general conclusions about all people and all plants of that type. Since then, those methods have been widely applied to determine the significance of findings. But in many spatial applications, including the asbestos example, there is no question of reasoning from a sample to a larger population. Instead, every county has been analyzed. The assumption that instances of spatial data have been drawn randomly and independently from a larger population is often irrelevant. Another reason why spatial is special. Finally, we work today with data that have been created by observing the real world, and our instruments for measuring appear to be very accurate. We often forget that, quote, the map is not the territory, unquote, that spatial data are only a representation of reality, that all spatial data are approximate, generalized, and smoothed, and that what is missing in the data may sometimes be the most important detail. It is impossible to measure location exactly, even with the most sophisticated GPS instruments, and map making is both a science and an art. So uncertainty should always be a major concern of the analyst, in terms both of the data being analyzed and the results that have been obtained.